Thank you for those kind words, Mark. My facial hair really appreciates it. Yeah, so I want to talk to you all today about write once, compile lots, run anywhere. So one of the reasons I first came to Go was the ability to really simplify distribution of software, particularly command line interfaces. So being able to build a program, write the code once and then run it anywhere on all these different platforms. With Go, though, the thing is we're compiling to machine code, so we do have to compile lots for all these different target platforms. But this idea really sort of came into prominence with Java, right? With write once, run anywhere. And here's everyone's favorite, really recognizable mascot, Duke. Applause for Duke. Everyone loves Duke, right? Yeah, OK. Not really sure what Duke is. Definitely not a gopher. But if we're really going to talk about Java and about write once, run anywhere in particular, we need to go back in time to the 90s, right? So we're back in 1996 now, right? And Java 1.0 is just coming out, and everything's all about write once, run anywhere. So the idea here is that as developers, we'd program against the JDK or the Java development kit and write our code and then compile it into bytecode. And with this bytecode that is sort of like assembly language, but not really, that would run on the Java virtual machine, or JVM. But to package it up, you need to put it in a Java archive or a jar. And then you can ship it around. So we've got this really nice flow, right? You write code against this one SDK, and then you compile it to this format that is understood by many different platforms through the JVM, and you package it up into a jar, and then you're able to ship it around. So with this, we're able to take our code and we could run it in the cloud, right? Or we could run it on smartphones, or we could run it on laptops. It was awesome, except for this one tiny problem. It's that with all of these, you had to actually make sure that the JVM was installed first, right? So Duke rears his head again. So there was this extra pain for the user in that they had to install a JVM first. And you had to make sure as a developer that they understood they had to do this first. So we had the actual Sun Java virtual machine. But there were some others too, right? IBM had its own JVM. Microsoft had its own JVM. And Microsoft, being the Microsoft of the 90s, were extending the JVM to do a little more than sort of regular JVM. So we had a bunch of different JVMs. You weren't really sure which one your users would be using. They were all subtly different. Maybe some APIs were missing from one. Maybe one had extended the API a bit more. And then we ended up with this sort of this tribal voodoo knowledge about what you might have to do to get a program working. So it would be really common to say, oh, this application has to run on the IBM JVM because of the way that it does garbage collection. So the idea of write once and run anywhere, just through the fact that you had to make sure the JVM was there and there were different JVMs, well, it didn't really pan out. So it wasn't really living up to what was offered. So given all that, what does make for good multi-platform distribution? Spoiler, Go is going to hit all of these because this is a talk about Go. But we've got 4 points. Support for platforms you care about, simple to package and ship, no extra dependencies, and broadly compatible. So let's walk through them. The first one already was hit on a little earlier, right, with one of the questions. Here's the 44 combinations that you can have for running Go on. For me, the ones that matter are these three, right? Windows, Linux, and Mac OS. If I'm building a CLI, those are sort of the main ones I want to hit. Unfortunately, in this day and age, I only really have to worry about AMD 64 for the architecture. But the cool thing is that the Go program that you install, that you use to build your code, has a complete tool chain for all of these different combinations. And that's really powerful, as we'll see later. The other thing that I just sort of want to point out, because it's always cool and exciting, is that the little JS WASM one there. So we can say, you know what, hey, Go has support for the platforms you care about, right? Even if it's, even if it's, Solaris, hey, we got it. Go forward again. Boop. All right. So on to the next point about being simple to package and ship. This is about the tool chain and how easy it is to actually get going, right? So here we have our simple command to build a binary, right? Assuming that I have a main package in the current directory, I can go build, and I'm using like -o here to specify the name of the binary that I want to build. So this builds it for your current platform. And for me, on this laptop, that's Darwin, 64-bit, so Mac OS. And you can check it out with the file command. And in case you ever forget what computer you're sitting at, you can use goenv and do some grep. Hit me up after the talk if you have a better grep command than this to get out the detected GoArch and OS that you're on. What's kind of neat is that there is this GoArch and host, or the host variants of them, and the usefulness of that is the host one is where you actually are, right? So it is the host system. Where that comes into play is when we start overriding the values for GoOS and GoArch. And now we can build applications using the built-in tool chain for any of the platforms to do cross-compilation. So here, cross-compiling and building a 32-bit Linux binary on a Darwin machine. Pretty awesome without needing to install a full separate tool chain for it. And it's just as easy as using my regular sort of workflow for it. So I'm going to put this up there, though. It's nice and simple to do that, but if you want to do cross-platform distribution, you're doing 2, 3, 4, 5 different platforms, and then you're going to need to script out the different environment variables. So GoReleaser is something that'll take care of that for you. The fun thing about putting this up is it's a good excuse to actually get a QR code in a slide, because QR codes were created in 1994, so they fit the theme. Another aside about cross-compilation is Docker. So it took you a while to remember where that was from, right? So the neat thing about doing this cross-compilation is because it's the same tool chain that you're using, and with the advent of modules, we have really good caching in Go. So we can cache downloaded packages and cache the compiled archive files before they're linked together. So if I do something like build on my Mac laptop for Linux AMD 64, which is what I'm sort of de facto for Docker here, build my binary first, and then just have a really basic Docker file, and all it does is copy that binary over into the container, and then do my build. For a development process, this gives you a really tight inner loop, because you're able to reuse the caching of the downloaded modules that you share between your host system and your Docker system, and you're also able to reuse the cached archives. So instead of relying on Docker layer caching, you can get a little more fine-grained by using something that's aware of the language that you're using. Cool. So with cross-compilation, into a single binary, simple to package and ship. So no extra dependencies. Sort of hit on the first point, by virtue of comparing to Java, is that we are compiling to native code, so we don't have to worry about installing an interpreter or some kind of VM on, for our users, right? It's it kind of can't be overstated, like how much of a benefit this is, especially if you're building something that isn't necessarily developer focused, right? Then your users don't have to understand what the JVM is to get going with your program. And the second point, is that when we Go code is statically linked, so everything's all in one binary, sort of. Put a little asterisk there for 2 points. The first point about this is asset bundling. So if you are distributing something, chances are that you're not just distributing the code. You've got some other stuff you want to send along with it. So you've got your code, and then maybe you've got some images that you want to send along with it, or some documentation, or you've got some template files, right? And with asset bundling, you take those and you put them together into one binary. The way we typically do this is by doing like a generation step where we take our asset files and convert them into source code, where it's just using into like constant vars, and then using those to fill the data segment of our built binary. So here's where I give a shout out to our MC and try packager for this. It's a cool program for doing this asset bundling. There are a few other options, but what I like about Mark's is that he's made it module aware, so you can access things sort of relative to your modules, which is cool. And another fun fact, just like QR codes, Mark Bates was also created in 1994, right?
Not even close.
No, I better.
I appreciate the age.
Oh, I'll have to get better at fact checking for these presentations. Cool. So the other caveat for static compilation is let's look at this output. So here I am building for Linux AMD 64 like I've done before in this presentation for my Darwin system. Check the file output. Cool. It's we've got a Linux executable. What happens when I do this on a 64-bit Linux machine? So do this output here, check the file for it. Kind of similar, but here's the 2 points that here's the difference that I want to point out, is that this one's statically linked and this one's dynamically linked. So if we look a little deeper in that, and we do just rename it here, and we look at the linked libraries with this, you can see a few base ones here. So this is actually a program that was using Packager. So even though it's something that is like not necessarily obviously using native system libraries, there are chances that you'll get them pulled in. So the two here are just for actually handling the dynamic linking, like loading shared object files. And then these other two are just the POSIX thread library and libc. So really standard C libraries, that you can kind of assume will be available. But what happens when you assume? So if we take this file that I built on an Ubuntu Linux machine, and I try to run it on Alpine Linux, here's what happens. Not found. And so the typical thing you do is run it again. Like, where is my file? Fortunately, it's deterministic. And you look at this, right? And I have to say that I learned this the hard way about what actually happened here after distributing some software. But if we look at this and it's like, oh, there must be some subtle difference in this message. Like it looks like the file's not found, but there must be some subtle difference in the output that I'm just not really understanding, right? Because how can the file not be found? I know it's there. So let's just try a file that's like totally not there. Same output, right? So what's going on here? Now this is because it's dynamically linked and because I built it on Ubuntu and I'm now running it on Alpine. And the hint is actually, or the giveaway here, is this interpreter line here. So the fun thing about the ELF format is it has this field called PT interp, where you define the interpreter for your distributable. And it's specifically about the interpreter for handling loading of shared objects. So when this file gets loaded, the first thing the kernel does is it actually treats it the same way it would as if you had like a script file with a shebang at the start. And it tries to find the file that would interpret this or load the shared objects. And on this Alpine system, this file is not there, so not found. Yeah, it's like super obvious error message. So the thing that's going on here is a little quote that I pulled out of the page on Seago. And it's that Seago is enabled by default when you're doing native builds. So if your host platform or operating system and architecture match the target operating system and architecture, you'll have Seago enabled. And Seago is this, is a really awesome, really powerful way to communicate between Go and C, to consume native libraries. But if you don't need it and you're having it included, it can be a real surprise. Advice here is if you're doing cross-platform distribution, start by disabling Seago. You can avoid some of these headaches of having subtle differences between Linux distributions. And starting with it disabled means that the first time you pull in a dependency that needs it, well, it'll blow up when it's compiling. Also worth noting that GoReleaser doesn't support using Seago, so if you start that way, you're kind of buying into this idea by default. So, no extra dependencies. We can bundle everything together. Let's look at the last point. Broadly compatible. So what do I mean by this? I mean that the behavior that you're going to see is consistent across platforms, and that the features and packages you want to use are available across all platforms too. So this is the case where if you're running, distributing something for the JVM and you see differences in garbage collection between JVMs, and that affects the performance of the program, or just having libraries that are not built or supported for different architectures. So the benefit or the way that we get this from Go is because we do statically compile everything and put it all together. And I'll say that I'm saying this tongue-in-cheek, but I think that this is the bright side of not invented here syndrome in Go. We have a huge amount of things like compression libraries and cryptographic libraries that in many other languages would be linking to things like OpenSSL for them, or libsodium for other crypto functions. And instead we have them, we have the work of hardworking and dedicated individuals who have written these for us natively in Go, and in some cases in assembly as well, to get the compatibility and performance that we expect. And it's really awesome. So it means that you can do something like use some of these different crypto functions and not have to worry about which version of OpenSSL your user has, or try to get them to install a different one, or try to ship libsodium along with it. But there are cases when you do want to do some platform-specific logic, where you do want to have some differences between where you're distributing. And that typically comes down to cases where you're interfacing with the operating system or with the architecture. So one of my favorite examples of this is actually from the crypto X509 package, like in the standard library. And what's done here is that the standard package actually falls back to the host platform's like logic for verifying CA certificates. So if we look at our sort of standard use case in this, which is the verifying a certificate, right? We got this, the function or the method for it, and then we can look at the ops for it. And there's this field, the root cert pool. And if it's null, then we use the system certificates. So like it's sort of implying here that we're going to fall back to whatever the system does. If we look at the code that actually handles this, there's this little block here that looks to see if these roots are nil, and then also checks for runtime.goOS to see if it's Windows. And if it is, it does different logic, right? Instead of actually looking at the system cert pool in a way, it's doing this different func, which is to do the system verify logic. So we have this one way of doing platform-specific logic, which is to examine runtime. And I'm just going to dive in a bit more on this, on system verify, but for the other platforms, like you can get further into actually looking at like loading the system certificates or and how they do them differently. But in this specific case for system verify, this func is declared in a few places, right? It's in multiple files. And so by default, if we tried to compile something like that, it would fail, right? We'd have clashing definitions here. But the way that we get around that is with build tags. So build tags are like implicit and explicit. So we have a bunch of implicit ones, which are our operating system, our architecture, and other things like you can see the Go version as well. And then you can specify some explicit ones if you have like arbitrary logic that you want to be able to sort of switch on. So that's sort of how they feed in when you're compiling, but how do you use them? In this case, we have the two files, and the second one, the Windows one, is suffixed with _Windows. And if you have a suffix on a file name that matches a tag that sort of satisfies the constraint for that file to include that file, which is a pretty elegant way of being able to specify these things. So a fun fact is that test, so you have your _test file, is not actually a build tag that's specified. So if you try to use tags for including test logic, it's not going to work. But the other way to do this, and the way that this root Unix file is working, which like Unix is not, it's funny to say Unix isn't an operating system, but in the case of the available operating systems for us, it's not a defined one. So how does that file get like excluded when we're using the Windows one? And this is with specifying your build constraints as like a comment declaration. The logic for this is super easy to understand and really easy to remember. Here's a great example of that, a poll that Francesca ran a little while ago. And you can see that everyone's pretty much split on it, right? Around what the actual syntax is. And all of the options were wrong anyways. So it's a good thing that we don't have to use these like all the time. But I will just run through how the tags work actually. So this is the comment declaration plus build. And this specifies the constraints that you need to satisfy, so the tags that are listed when you're building. And if you have a space, it's an OR. So this in a file would mean that it would be be built either for Linux or Solaris, so on either of those platforms. If it's a exclamation mark, it's a not. So this file builds on everything but Darwin. And a comma is an and. This is probably where you get thrown off, right? Because commas feel like ors rather than ands, but maybe that's just me. So here we're saying like Linux and CGO. And then if you have multiple lines, they're all ANDed together. And this is how you can sort of build like complete Boolean logic, because otherwise with the commas, it's, it's not possible to do it without the separate lines. Great, so looking at the actual Unix file for CA certificates, this is the line here. So it's just explicitly saying build it for all these Unix-like things. And there's our friend JS Wasm again, showing up, sort of looming over us. All right, so back to our 4 points again, and we can check off the last one. And you know what that means for multi-platform distribution? Go is thumbs up. All right, thanks, everybody.